I'll be talking about representative sampling of taxa on a phylogeny with a tool that we developed called PARNAS. And this is a collaborative work between the flu crew at USD ARS, where swine influenza research group, and the computer science department at Iowa State University. Just gonna grab a pointer. Okay. So quickly, goals and motivation for this project. We wanted to develop a method for objective and flexible sampling of taxa on a phylogeny, and most importantly, it needed to be representative of the diversity that we observe on the phylogeny. And the primary motivation for that was microbiology and virology in particular. So there we typically looking at trees, or routinely looking at trees with 10,000 or sometimes 100,000 taxa, and in many other areas of research too. So it gives great insights into diversity, but also we need to perform phenotypic characterization of virus strains or bacteria strains, and that can be only performed on a subset of taxa, so we need to objectively select some. And so this is an example of a problem we can be looking at. This is a screenshot from NextStrain. So this is a SARS-CoV-2 phylogeny. And so here you can, here you can see that we have lots of familiar names, lots of familiar clades, and many detections within different clades. And if I ask you, can you select 5 strains here for objectively for characterization, it can be quite a challenge, and so we need to develop some framework to do for doing this. Okay, and so other applications of representative sampling on a phylogeny could be just downsampling. If you have a large genetic data set, you might want to downsample it, large phylogeny downsample it to perform some computationally intensive Bayesian analysis, or just visualize the phylogeny while preserving as much diversity as possible. And then also kind of hinted towards that for vaccine strain selection, we might want to stick some of the selected strains into vaccine. And on the other end of this is biodiversity conservation. So how do we propose to solve this problem? We want to, given a phylogeny, and we want to choose K representative taxa on the phylogeny so that the total or the average distance from all the other taxa on the phylogeny to the representatives is minimized. So from every taxon to the closest representative. And so this is formally known as a K-Medoids problem. And if we look at it, if you try to visualize it, so let's say we're given this this set of data points. So this is we have 3 diversity groups here, and this is not a tree, of course, but you can imagine that those points here are taxa, and the distances here represent evolutionary distances. And so then we have this 3 groups here, and if we want to select with K-Medoids 3 representatives, it might look something like this, labeled by 1, 2, and 3. And so we just select the centers, the most representative points here. So formulating this problem, we are trying to select a subset of taxa S, so that the total distance from all the taxa to the closest representative within S is minimized. And so this is how it can look on an actual phylogeny. This is swine influenza clade that is endemic to the US. And here we asked PARNAS, so this is an actual output from our tool, and we asked the tool to select 3 strains that would be representative. And so you can see here that it simultaneously clusters the taxa and also selects representatives from those clusters. Okay, so how do we solve this problem? I need to mention that this is not the first time this problem was considered in phylogenetics. It was first probably considered by Faith in 1994 for biodiversity conservation, and then more recently by Matson et al. In 2013 in systematic biology for biodiversity conservation, but also they considered it for epidemiology and improvement of HIV phylogenies. And so in Matson et al. They actually implemented this as a tool called ADSL, average distance to the closest leaf, which is exactly what K-Medoids is. And it's available as a part of the p-placer suite of methods. And so they implemented actually 2 algorithms in there. They have an exact but exponential dynamic problem solution, and also adaptation of a PAM heuristic. So PAM heuristic is typically used for solving k-medoids on Euclidean spaces, and so they adapted it towards tree space. And so, unfortunately, or fortunately for us, Matson et al. Did not know that this problem is actually efficiently solvable on a tree. And so this result comes from a long time ago. It's within operations research, people were looking at similar problems. And so the most relevant to us work comes from Tamir in 1996. And they considered a problem called p-medium. And actually, Tamir considered a generalized version of this problem, which is very, very convenient for us. So if we play around a little bit with the problem that Tamir solved, we can reduce it to this form. So this is our new objective function. This distance from taxon to the closest representative is what we had before. And now we have two more components in here. We can, so every taxon can have an associated cost of it being selected as a representative. And also, very importantly, we have this transformation function f here, which is also can be unique to every taxon. And the only condition on the function is that it needs to be non-decreasing. And so what it meant for us is that we can implement multiple extensions to k-medoids. And so one, the obvious one, we can put weights on taxa. So if we have taxa with higher weight, we want them to be represented more than others. Then we can also quite flexibly switch taxa 1 and alpha in the phylogeny. So for example, we might have some taxa that we want to be represented within selections, but we don't want them to be selected as representatives. Or the opposite is some taxa we don't care whether they're represented or not, but we do allow them to become representatives. Or we can just entirely switch off some taxa on the phylogeny. And so we regulate in PARNAS using regular expressions. And then additionally, we can account for prior representatives. So for example, if we previously characterized some viruses, we can take that into account, and so we can select new representatives so that the old ones and the new ones can work optimally together. Okay, and so this is now the most exciting, at least to me, extension. We can actually fine-tune what we mean by representation and what we mean by coverage. So this is the original problem that we have. So let's say this red point here is a representative, and this black taxa here is what it is representing. And so in our original problem formulation, the contribution of each taxon to the objective function is the distance to the representative. And since we're now accounting for weights, it's scaled by the weight here. And so we can fine tune that, and we can introduce a coverage radius. And so it's kind of shown here in blue around the representative. And so for the taxa that fall within the coverage radius, the contribution is now simply 0 because they're covered. And then for others, we can still care about them, and we don't want them to be too far away from being covered. And so we measure how far they are from being covered, and again scale it by the weight of the taxon. Alternatively, we can solve a binary coverage problem. So we at each taxon is it covered or not, and then the contribution of taxa that are not covered is simply is their weight. And so that way, if we're solving this problem on the tree, we want to select k taxa so that as many taxa as possible are covered within this fixed radius. Okay, and so this kind of leads us to a related problem. What if we don't want to actually specify a fixed number k, but we want to know how many taxa do we need to cover entire phylogeny, so to cover all the tips on the phylogeny. So we want to know the minimum number of taxa needed to solve this problem. And again, we want to be flexible. We want to account for potential inclusion-exclusion constraints, and also for prior representatives that also could be already covered in some of the diversity. And so this can be a very useful problem if you want to eliminate redundancy on the tree. We can fix a small evolutionary distance as a radius, and then we optimally reduce redundancy in this way. Additionally, and this was primary motivation for implementing this radius here, we can find antigenically advanced viruses, and also their applications into vaccine design, and I'll talk about that in a bit. Okay, so quickly algorithmic complexity of all this. So the original algorithm by Tamir in 1996 had both worst case and best case complexity of kn squared, where k is the number of representatives that we want, and n is the number of taxa. And then in PARNAS, we implemented a few algorithmic advancements. And so we still have the worst time complexity of kn squared, but the best time complexity improved to kn log n. So this kn log n is achieved if your tree is nice and balanced, and you drop down to kn squared if it's a more caterpillar shape. And so if you have something in between, then your complexity is something in between. And so in simulations, we saw that as compared to the original Tamir algorithm, we do get about at least 50 to 100 times improvement in runtime. And also implemented algorithms for solving the complete coverage problem, and they run in n squared. But I do believe that the best case, at least base case, complexity can be improved to n log n, but we're going to work on that next. Okay, so some experimental results. This is scalability. So we wanted to compare PARNAS with ADCL, which is a direct counterpart. And so as I already mentioned, ADCL has two core algorithms in it. One is ADCL full, which is an exponential dynamic programming solution, and ADCL PAM, which is a heuristic. And so we didn't do anything fancy, just simulated some bird death trees with up to 4,000 taxa and 10 replicates per fixed number of leaves. And so this is the runtime comparison with a number of taxa growing. So I'm showing you ADCL full in red, that's the top line here, ADCL PAM in green, a middle line, and PARNAS in blue at the bottom. And so we can see that the PARNAS is more scalable than the other two methods, quite significantly here on large number of taxa. And nicely enough, it seems to be growing almost linearly on this data. So what's most encouraging here is that, as I already mentioned, ADCL PAM is an inexact heuristic, and while in PARNAS we implemented an optimal algorithm, so it's nice to see that we're beating the heuristic too. And so this is just complexity in terms of scalability, in terms of number of representatives. So we can again see here that we are faster than the other two algorithms. Okay, so now this is an application to real data. Wanted to apply PARNAS to swine influenza diversity in the US. And so to give you some background on this, swine influenza A virus has at least 18 co-circulating clades. They're all antigenically distinct and are all endemic to the US. And so this is a lot of diversity, and it's a big challenge for vaccine development. But there's also one known fact there that if you're looking at sequences and you have 5% divergence in the HA1 protein of influenza A viruses, then it's known to correlate with immune escape and antigenic advance. And so we wanted to leverage that within PARNAS and use it as a radius. So we're going to use it as a distance threshold and a radius within the selections. I'm going to skip over some final details and going to give you an overview of this kind of, give you an idea of what diversity we're looking at. So the two figures here, one for H1 subtype in swine and H3 subtype in swine. And so we have different colors here represent antigenically distinct clades that are co-circulating. I think this is just a 6-month window of submissions. So we're getting lots of different clades in H1s and also some more diversity in the H3s. And so this is the results, and let me just tell you about the experimental setup, what we wanted to achieve here actually. So we used PARNAS to select for H1s 2, 4, and 6 representatives, and then we wanted to see how much coverage are we getting. So for each, so we're looking at the representatives and seeing how many of the other sequences within a 5% threshold are they covering, and that would kind of indicate of the potentially vaccine effectiveness. And then so we're doing the selections for different years, so starting with 2016, and then we're looking how the coverage wanes as we go to the next years. And then we want to pick up kind of a general pattern here, so we do the same for 2017 and 2018. And then similarly for H3s, but we have less diversity there, so we're looking at 1, 2, and 3 representatives. And so what we saw was that with 6 representatives in the H1s, you can cover nearly 90% of overall diversity. and that also generally stayed very high in the next year, so above 85% for all years that we looked at, and then it starts to drop after that. And then for H3s, we saw that 2 or 3 strains might be sufficient to cover 80 to 90% diversity, and that actually remained quite relevant and stable, or could remain quite relevant and stable for multiple years. And so what it kind of suggests is that potentially 6-component vaccines in H1s could be efficient in swine influenza, against swine influenza, and so it would be great to test it eventually. But that does suggest some vaccine practices here. Okay, so to summarize everything, so we are working with large genetic data sets, and we often need to downsample them while preserving diversity as well as possible. And so that was the idea that driven PARNAS. And so we are simultaneously clustering the taxa and phylogeny and selecting representatives there. And so while doing so, we can account for taxa weights, prior representatives, and then the coverage radius to fine-tune what we mean by representation. And then we can also flexibly constrain the pool of representatives and also what we represent. And then we did see that it is faster than ADCL, and also ADCL does not account for these nice items here. And then we used PARNAS to look at the landscape of swine influenza in the US and understand and kind of influence potentially some vaccination strategies. So this is a link to our GitHub page, and it's available in PyPy. And so lots of people to thank. This is us at the Flu Crew, and want to thank Davis Anderson, Amy Baker, and Zeb Arensi, who are all here, and people at Iowa State University, Oliver Ornstein, Sankit Bagley, and Sidhan Grover for contributing to this project. And our funding sources use the ARS, NHCR, and CDC. Thank you.
So I have a question if no one else does, which is, I found your sort of discussion of how this implies for vaccines very compelling. Can you talk a little bit more about how it would be used in the context of biodiversity?
Yeah, I didn't think too much about that, but I guess the faith. So I'm guessing still phylogenetic diversity is used frequently to evaluate species diversity, and there are lots of problems associated with phylogenetic diversity. For example, it likes to select long branches that could be just errors, picking up errors, or something that is not representative. And so this would, and I think in Matson et al. They argue that something like chemidoids would solve that issue, but I guess yeah, you need to think about functional diversity there as well, but it could potentially solve the issue related to phylogenetic diversity.
But it's not being used right now to decide which species go on which levels of diversity risk, for example. Or
I do not believe
extinction
so.
risk.
No, I don't think so. I think it wasn't, so you can do similar things, just not on a tree, and you can then account for functional diversity and things like that. And I do believe that approach was implemented in the diversity package by Faith, so that might be used. I do not know how they solve this problem, but it is more like Euclidean space rather than.
Do you or does anybody look at sort of this kind of sampling in a almost a bootstrapping perspective? Supposing I want to build a tree and I have too much data, so I subsample. Am I better off if I do that many times, and how many times should I do that?
Yeah, no, it's a good question. I think here we are selecting objectively and always the same set because it's just a non-random procedure. So I'm guessing for bootstrapping, people would prefer it to be quite random, but it could be somehow mixed in. I'm guessing with randomization and then selecting, maximizing representation. So yeah, could be something there.
We'll give you something to do when you get home.
Yeah, I get it.
We have other questions for Andre? Ah, we have an online question. Okay, we have a question from Siavash, who says there's a linear time method called tree cluster for a somewhat similar problem. Just wondering if the authors have known about it and considered comparing to it.
Wow, did not know about that. Thank you, Siavash. I highly doubt that this problem is solvable. This particular problem is solvable in linear time. Maybe they're doing some approximation there, but we'll definitely look into that. Thank you.